Welcome everybody back to the 8th chapter and second part of the Crystal Clear Electronics video series.
Viktorral folytatjuk az astabil áramkörök bemutatását.
I hope you're ready to continue the assembly. In this video, we will implement a similar function, but with a 555 integrated circuit instead of a transistor. But why is it good to use generally integrated circuits instead of discrete components?
That's because you get the same function with far fewer parts, so you get the same function in a smaller size. It's also easier to design because the core of the circuit has already been designed for you, and it's easier to assemble and manufacture because you only need to fit one part instead of a whole bunch of parts. Let's take a look at the use of the 555 IC.
Square waves are required for many applications, but the transistor solution occupies a large space on the one hand, and its frequency is also sensitive to heat and supply voltage on the other hand. Because of this, and in order to unify a wide range of functions, in 1971, the 555 IC was created, which is still very popular to this day. Build the circuit shown in the figure on your breadboard, then add 12 volt power to the circuit using a lap power or power plug. The LED on the output will blink approximately once per second. Try changing the blinking frequency again by replacing the components. You have to pay attention to make sure that R1 is not smaller than 1 kilo ohm, otherwise the IC may be damaged. First, replace resistor R1 to a value of 68 kilo ohms. You will notice that the LED is on for a longer period of time than it is off, and the blinking speed is slightly reduced. Replace the 1 kilo ohm resistor in place of R1, and replace C1 with a capacitor of 22 microfarads. The blinking speed will then be halved, while the LED is lit up for about the same length of time as it is not. If you decrease the value of R2, the blinking will become faster, and the time difference between the two states of the LED will increase. We can conclude that the frequency of the LED blinking depends on the value of R1, R2, and C. The ratio of the times of the LED states depend on the value of R1 and R2. Let's see what's in this integrated circuit. Inside, there's a voltage divider consisting of 3 resistors of equal value, RA, RB, and RC. In their connection points, 2/3 of the power supply voltage and 1/3 of power supply voltage can be measured from top to bottom, which in this case means 8 volts and 4 volts. Then, there are 2 voltage comparative modules that connect the supply voltage to their outputs, hereinafter referred to as logic 1 state, if their positive inputs have higher voltages than their negative inputs. In all other cases, 0 voltages can be measured at the outputs, hereinafter referred to as logic 0. The IC thresh terminal, or threshold, is connected to the positive input of one of these modules, and its negative input is connected to the resistor divider's 2/3 point. So this comparator will have an output of 1 if the voltage on the thresh pin is greater than 2/3, in our case, greater than 8 volts. The positive pin of the other module is connected to the 1/3 point of the divider. The negative pin is connected to the IC leg marked with the trig title, which means its output will be 1 if the voltage on trig, or trigger pin, is less than 1/3 of the power supply, or less than 4 volts in our case. The output of the 2 voltage comparative modules is connected to a so-called RS storage element. This element is capable of maintaining its output voltage 0 or 1 state. The state change between states is determined by the voltages 0 and 1 on its inputs. If S, or set, is set to 1, then the output is set to 1. If you have 1 on the R or reset input, the output is set to 0. In the 555 IC, this means that the output of the RS container is set to 0 if the voltage on the IC thresh pin is higher than 2/3 of the voltage of the power supply, and it gets to a 1 state when the voltage on the trig pin drops below 1/3 of the power supply voltage. The IC output is connected via an amplifier to the output of the RS container to ensure that up to 200 mA of current can be flown on the output of the IC or on the outleg. The IC includes a transistor that switches on when the output of the RS flip-flop is in the 0 state. This negated operation is accomplished by a unit represented by a triangle and a small circle connected to the base of the transistor. The IC discharge or discharge pin is connected by the transistor to the pin of the IC ground. How does the IC work in the Astable circuit? Initially, the voltage of the capacitor C1 is 0 volts. When the power supply is connected, the supply voltage can be measured on the IC output, the LED is on, since the voltage on the trig pin is lower than 1/3 of the supply voltage, hereinafter referred to as 4 volts, and the S input of the flip-flop is 1. The capacitor starts charging via resistors R1 and R2. As soon as the voltage reaches 4 volts, the lower comparator output will be 0, but the R input of the flip-flop will still be 0, so the IC output will not change. The process described so far takes place only when the circuit is turning on. Further events will be repeated periodically. The capacitor's voltage will increase further up to the 2/3 of the supply voltage, hereinafter referred to as 8 volts. At this moment, the output of the top comparator changes to 1, which makes the output of the RS flip-flop to 0, and 0 output voltage can be measured at the IC output, and the LED will be off. At the same time, the transistor is turned on, and it connects to the discharge pin on the ground, which causes that current flows from the capacitor through R2, that is, it starts to discharge. That's the origin of the name of the discharge pin. The capacitor's voltage drops down to 4 volts. At that time, the lower comparator output will change to 1, resulting that the output of the flip-flop will be set to 1. The internal transistor closes, and the connection between the discharge pin and ground will be terminated. At the same time, the power supply can be measured on the IC output, so the LED lights up. Let's now replace R2 with the 1 megaohm resistance. This will increase the time of change in output. Use your multimeter to measure the voltage at the terminals of the C capacitor. You'll experience that while the LED is on, the voltage will increase from 4 to 8 volts, then the output will change, and the voltage will decrease until it reaches 4 volts, and then the process starts from the beginning. The two threshold voltages are exactly 2/3 and 1/3 of the supply voltage, so the circuit operates as described above. The change in voltage at the IC output depends on the charge and discharge time of the capacitor. During charging, this time is determined by the values of R1 plus R2 and C. At the output, the supply voltage can be measured, the LED is on. Only the values of R2 and C are authoritative during discharge. The output voltage is then 0 and the LED is off. This means that if the resistance of R1 is not much less than the resistance of R2, then the duration of the on and off states will not be equal. You also experienced this when R1 and R2 were 68 kΩ resistors. The ratio of the two periods can be calculated by the following formula, and by substituting the numbers, the result is 2. This means that the LED lights up twice as long as it doesn't. If the value of R1 is much less than the value of R2, then the two periods will approximately be equal, and the frequency of the output will be determined mainly by the value of C and R2.
Now let's reconfigure our circuit to the original layout. Replace the 22 microfarad capacitor with the 10 microfarad.
10 mikrofaradra.
Change back our 68 kΩ resistor to 1 kΩ.
1 kilómra.
And our 1 megaohm resistor to 68 kΩ. This restores our circuit to the original layout. Now add another LED and a resistor connected between the 12 volt supply voltage and the output of the 555 IC.
Out kimenete közé kötünk be.
Our circuit will then flash in the same way as the transistor Astable circuit shown in the previous video.
In this chapter of the curriculum, you've learned about the two types of implementation of the Astable circuit. Both solutions are based on the time required for a capacitor to charge or discharge through a resistor. You also learned that the time depends on the capacity and the resistance. In fact, we use this method to so-called measure time. The voltage at the output of the Astable circuit changed between two values, called logical 1 and logical 0 states. This also means that the output can be considered as a digital signal. In the curriculum, this was the first circuit that actually did something independently. In this case, it produced a digital signal and flashed two LEDs.
With this summary, we come to the end of our video. Thank you for joining us for our episode called Astable Circuit. We hope that you have learned a lot from these videos and that you will be able to use it in the future. The curriculum can be downloaded in PDF format from crystalclearelectronics.eu and in Hungarian from kristaltisztaelektronika.hu, and you also can find a mobile application for Android and iOS platforms under the same name. You can also follow us on Facebook, where you will be informed about the latest news. See you soon in the next video. Goodbye.
Goodbye.